In this video, we discuss finding a power series representation for a function. Earlier, and I think it was our first video over power series, we had geometric power series. We noticed that as we move from term to term for the given power series, we were always multiplying by the same thing. And we said, if that's true, well then I can think of that as a geometric power series and I can find its sum. So this is kind of going backwards. Instead of giving you a series and asking you for the sum of the series, if it happens to be a geometric power series, in this case, I'm going to give you a function and ask you to find a power series representing the function. Now we're going to learn a method that works for most functions, which is Taylor series. We're going to find Taylor and Maclaurin series for functions later, but initially we're just going to stick to those geometric power series. So if our function looks like a geometric series, looks like the sum of a geometric series, so it can be written in this form: a of x over 1 minus r of x, where a is a function of x and r is a function of x. If our function can be written this way, then we can write it, or then we can represent that function as a geometric power series. Okay, so here's our first example. Now again, we're going to find a way to represent functions that don't look like this in later sections, but let's start with functions that look like that. Let's say I've got f of x equals 2x squared over 4 minus 5x. Now you might be saying to yourself, that doesn't look like that, but it's close, right? The only difference between this form and this form is that I've got a 4 here and I have a 1 there. I would really like for that I'd really like for that 4 to be a 1. And actually, let's change it up even a little bit more. So it still looks similar to that, but I've got a 4 where I want a 1, and I have a plus where I want a minus. Well, that's easy enough to get rid of, and easy enough to adjust that for just algebraically. If I want to make that a 4, I can divide the numerator and denominator by 4. Just like we've been doing every time we get rid of those indeterminate forms, by dividing by the highest power of x or n, and that would always give us that constant that we wanted. But that's exactly what we're doing here. I see a 4, I'm like, I don't want it to be a 4, I want it to be a 1. So just take everything and divide it by 4. That's legal as long as I also do the same thing in the numerator. So we'll simplify that numerator. 2 over 4 is 1/2. In the denominator, I've got 4 divided by 4 is 1. And then 5x divided by 4, I could write that as 5 over 4 times x. So we're good there. And now this is almost in the form of that. But I've got a plus sign where I need a minus sign. Well, that's easy to adjust as well. So we will, if I want to add, if I need to subtract something, and it looks like I'm adding it, I'll just change that addition sign to subtracting a negative, because subtraction is just adding the opposite. Now it's probably been a while since you thought about that, but it is. If I'm subtracting a negative, that's adding the opposite, which is just adding. So now this looks exactly like that. All I had to do was a little bit of algebra, dividing by the right thing and then writing that addition as subtracting a negative. And now I can identify a of x. It's 1/2 x squared, and I can identify r of x. It's negative 5 over 4 times x. And now that I've identified A and R, I can write it as a geometric series. So let's just remember this fact, recall this fact. If I have the sum as n goes from 0 to infinity of A times R to the n, that converges to A over 1 minus R on the condition that the absolute value of R is less than 1. So when I've written this way, it looks like that. I can identify A, I can identify R. Once I've done that, I just have to go backwards. If it's written in this form, I can write that as a geometric series. But of course you have to remember that it only converges to this function when the absolute value of R is less than 1. So let's do that. It's the sum as n goes from 0 to infinity. It's just the general form that we use for our geometric series of A times R to the n. And A is 1/2 x squared, and R is -5/4 x. And you could leave it like this. You would be done. If I asked you for the power series representation of f, you could be done here. But typically we want to be able to differentiate these series and anti-differentiate these series later. So we like to do a little bit of algebra first. If I'm taking the derivative of something like this, I don't want to have to use the product rule for every term. Derivative of the first times the second plus derivative of the second times the first. Like, that's much more complicated than is necessary. I could just do some algebra first using exponent properties, write this in a cleaner form, and then when I take the derivative, it'll just be the power rule, taking the derivative term by term, which we'll see in a little bit because we haven't talked about derivatives yet. But yeah, the idea is we want to simplify this so that when we take the derivative later, we don't have to use any of our more advanced differentiation rules. So I've got 1/2 x squared, I'm leaving that alone, and I've got this fraction times x to the nth power. Now there are a couple of exponent properties that we can use here. If I have a times b and I'm raising it to the nth power, well, that's the same as a to the n times b to the n. Or if I have a over b and I'm raising that to the nth power, I can raise the numerator to the nth power and the denominator to the nth power. So putting those together, I've actually got 4 implied factors here. I've got a 4 in the denominator, I've got a -1 out front, I've got a 5 in the numerator, and an x in the numerator as well, or you can think of it as just a separate factor. Either way, but that nth power has to apply to all of those. And through a combination of these two rules, we would see that it applies to all of those. So I'm going to apply my nth power to every factor inside, and I'm thinking of these as 4 separate factors. So I've got -1 to the n, then I'll have a 5 to the n, then an x to the n, and in the denominator I have a 4 to the n. Okay? Now it's still not as simple as it could be. I'd really like to have this as a constant that depends on n, times x to some power. So I'm going to multiply this x squared and that x to the n together. All the rest of that is a constant, so I can factor that out. And then this, I've got x to some power times x to a different power. That can be simplified using this rule. Remember, if we're multiplying like that, the bases are the same, you add the exponents. So this is x to the 2 plus n, or n plus 2, whichever you prefer. Okay, so that's one simplified form of this function as a power series, and the power series is centered at 0 because of the way I chose to do this. Because I had the 1 here and I was subtracting the negative, I don't have an x minus a constant in the parentheses. So this is going to be the sum of infinitely many zeros when I substitute in n equals 0. Or excuse me, x equals 0. Okay, so let's say the question said, Find a power series representation of f and of course, anytime you do that, you also want to find the interval of convergence. And while we're at it, let's get the radius of convergence as well. Okay, so we found the power series representation for f, but remember, this is equal to this original function, 2x squared over 4 plus 5x, on one condition, on the condition that the absolute value of r of x is less than 1. So these are equal when the absolute value of r is less than 1, because that's when a geometric series converges, and this time our r of x is negative 5 over 4 times x. When I take the absolute value, that negative will be gone, so I can factor out the 5 over 4. And to get the absolute value of x by itself, I'll multiply both sides by the reciprocal of this. I wrote 5 over 4 twice. 4 over 5. The 5's reduce, the 4's reduce, and now I've got the absolute value of x is less than 4/5. And if the absolute value of x is less than a positive number, that means the x has to be between the negative version of that number and the positive version of that number. And if you don't remember why that's true, you can always text me and I'll remind you. Okay, so that is our interval of convergence. Normally we write it in interval notation like this instead. And the radius of convergence is half the length of that interval, which I think we can all see that it's 4 over 5. So there's the center. We're adding and subtracting 4 over 5 to get from here to here. So r, that's half the length, it's that. Now if you don't believe me, you could always do this minus this and divide by 2. Or you can compare this inequality to the absolute value of x minus c it being less than r. C is what we're subtracting from the x, so it's 0, and r is on the other side of that absolute value, or on the other side of that less than sign. So those are your options. Okay, so if we have a function and it looks like a over 1 minus r, we've just got to do a little algebra to make it look like that. Usually it involves dividing by whatever constant is there. We never want to have an x in the denominator here as well. If this was written as 5x plus 4, I would switch it so it said 4 plus 5x, because I don't want x's in the denominator. In the power series, these, well, over here, these x values all need to be raised to positive powers. So I take this, I divide it by 4 to get the 1 there, and I change addition to subtracting a negative. And that gives us the series. We do a little algebra so that we can differentiate and anti-differentiate later without having to use more advanced differentiation or anti-differentiation rules. And then we say, okay, but when does it converge? That's very important. This actually gives us this, provided that we're on the interval from negative 4 over 5 to positive 4 over 5. Okay, one more example. They didn't tell us where this series had to be centered this time. They said, find a power series representation for f, any power series representation. So it made the most sense to find one that was centered at 0. Just made that into a 1 and changed that to subtracting a negative, and so it was centered at 0. But what if they gave us a function and they wanted the power series to be centered somewhere else? Maybe they're interested in approximating that function with a polynomial, or the partial sums of the power series, but maybe they're not interested in it near x equals 0. Maybe they're interested in the function near x equals 2. So they want a different representation. Let's do a problem like that now. Let's say someone asks you to find a power series representation of f of x, and I'll give you f of x in a second. But this time we want it centered at x equals, say, -1. And maybe we've got f of x equals 5 over 2x plus 3. Let's make it 2x squared plus 3. Oh no, let's not make it squared. Okay, so let's say this is it. Well, that kind of looks like a over 1 minus r. You're just trying to manipulate it so it looks like a over 1 minus r. That's the goal. So the first thing I would do is I would switch the order. A can be a function of x and r can be a function of x. And I don't want x's in the denominator, so I don't want to divide everything by 2x. I just want the constant to come first. So I'll call that 3 plus 2x. So it looks a little bit more like that with the constant over here and a function of x on the right. Now they've asked us to center this series at -1 though. Now in order for us to center the series at -1, well, remember what that would look like. If the center is -1, our series has to look like this. Some constants that depend on n, times x plus 1 raised to some power. Because if it's centered at -1, x equals -1 is the x value that should make this 0. So you would see a plus 1 there if the center is at -1, at -1. Okay, so I'm trying to get an x plus 1 in my r of x, because this is going to be something times r of x to the n. So I need an x plus 1 here, not just an x. Right now it's got an x there. Well, that's easy enough to make happen. If I want that to be an x plus 1, I can just force it to be exactly what I want. I'll just say, yeah, that's an x plus 1 now. If you're saying to yourself, that's not the same thing, you're absolutely right, it's not the same thing. But I can always adjust. If I make this x plus 1, that's fine. That's legal, as long as I also compensate for what I just did. Adding 1 in the parentheses here actually added 2 to the denominator. Do you see that? I've got the 3, it's still there. Over here I still have a 2. And 2 times x gives me 2x. And 2 times the 1, that's adding an extra 2 to the denominator. So to compensate for adding that 1, I'm going to subtract 2. I know you might think, well, in order to compensate for adding 1, shouldn't you subtract 1? Well, yeah, you're kind of subtracting 1, but then you're distributing the 2 to it as well. So we get this. Or if you prefer, you can also do it this way. If you don't like that reasoning. If you want sort of a way to always keep track of it algebraically, let's do it this way. We'll call that, make it x plus 1, and to compensate for adding the 1, subtract the 1 in the parentheses, and then distribute the 2 to that group and to that group. So you'll have 3 plus 2 times the quantity x plus 1 minus 2. That's the same thing I was doing there. I just didn't do it with all that distribution. Okay, because I'm adding and subtracting 1 in the parentheses, it doesn't change anything. I'm just adding a well-chosen 0. So now I've got 5 in the numerator, I've got a 2 times the quantity x plus 1 over here, and 3 minus 2 actually turns out to be 1. Hey, that looks a lot like this. But again, we're adding when we need to be subtracting, so we'll change adding to subtracting a negative. And now this looks exactly like that a over 1 minus r. Now remember, that's going to equal this series. You'll have a as a function of x times r as a function of x raised to the nth power, and n starts at 0 over there. Okay, So there's my A and there's my R. So this can be represented as a power series this way. It's the sum as n goes from 0 to infinity of A times R to the n. And that's my A. And that's my R. So A is 5 and R is negative 2 times the quantity x plus 1. And we're raising everything to the nth power. Now you're done, technically. If I asked you for the power series centered at x equals negative 1, this is correct. But again, we might want to differentiate and anti-differentiate this later. So I will distribute this n to all of the factors in the parentheses. And I know it looks like there are only 2 factors, but I want you to think of that negative as separate. There are 3 factors. That's a negative 1 times a 2 times an x plus 1. So we have 5 times negative 1 to the n times 2 to the n times x plus 1 to the nth power. And that's because if you have a times b to the n, that's the same as a to the n times b to the n. And that works for as many factors as you have. That nth power applies to all of the factors inside. So f of x, that is 5 over 2x plus 3, can be represented as this power series, but only some of the time it's represented as this power series when the absolute value of r is less than 1. And the absolute value of r is less than 1 when the absolute value of 2 times the quantity x plus 1 is less than 1. Now, the negative, when you take its absolute value, just becomes a positive 2, so you can take that out. And then if you divide both sides by 2, you get this. Now, through pattern recognition, through pattern matching, you can see that the center is 1 and r is 1/2. So we're going to center ourselves at 1 and we're going to add and subtract 1/2 from 1. That's one way of doing it. You could write your interval of convergence that way. Or you can just solve the absolute value inequality. If x plus 1 has a distance from 0 that's less than 1/2, then x plus 1 has to be between negative 1/2 and 1/2. So we'll subtract 1 from all 3 parts. Oops, I said c was positive 1, it's actually negative 1. And we get negative 1/2 minus 2 over 2 is minus 3 over 2, or negative 1.5 if you prefer. And then we've got 1/2 minus 1, which is negative 1/2. So our interval is centered at negative 1. We add 1/2 and we subtract 1/2. And that's our interval of convergence. So you can use fractions, or if you prefer, you can use decimals. And it's the same thing. Okay, so just as a recap, if you want a power series and it's centered at something other than 0, you want a power series representation for a function that kind of looks like a over 1 minus r. Not yet, but it's close. We're just going to do some algebraic manipulation. If it has to be centered at something other than 0, like negative 1, let's say it's centered at c, you need x minus c. Excuse me. If they're asking for a power series centered at x equals c, you need x minus c to be a factor of r. So you're trying to get the x minus the negative 1 or x plus 1 as a factor of r down here. And the way you do it is you force it to be exactly what you want it to be, and then you compensate for what you just did. So we added 1, and then we subtract 1 to compensate, and then you distribute the 2 and you get this. Or you can add 1 in the parentheses and say, well, what is that doing to the whole denominator? That's adding 2 to the denominator. So to compensate for adding the 2 times 1, I have to subtract 2 times 1, which is subtracting 2. Once you've got it this way, then you proceed in pretty much the same way as you did before. You identify a and r, and write this as the sum as n goes from 0 to infinity of a times r to the n, do some algebra, and then to find out where it converges, you just set the absolute value of r of x to be less than 1, and you solve for x. The radius of convergence is this minus this divided by 2, because that interval has length 2r. Or you could just do through pattern recognition. Once you get to this point where you've got a coefficient of 1 in front of the x, the number that you're adding or subtracting from 1 indicates the center. So if I see a positive 1 here, the center is negative 1. It's always the opposite sign. And the number on the right-hand side of that absolute value less than inequality, that's your r every time. So we're centered at negative 1, and then we add 1/2 and we subtract 1/2 to get the other 2 points on our interval, or to get the 2 endpoints of the interval. Okay, so that's what we get to do if the series looks like a over 1 minus r.